Welcome to the West video series. My name is Enrico Remigi and I'm the process modeler in the West development team. In this video, I'm going to show you how to simulate an inhibitory effect of a certain component. For the exercise, I'm going to use the model editor first to make some changes to my model library, and then the main West environment to set up and run a sample case. In fact, I have set up the sample case already. Now, what do I need to achieve this? Well, first I need an instance and a conversion model, that is a category in the West terminology, that includes a new component which can be used as inhibitory towards one or more groups of microorganisms. In a separate video, I have shown how to create a new category based on the original ASM1 and how to add a soluble component to that new category. So what I'm going to do now is continue, build up from there. This is how I'm planning to proceed and further modify my ASM1 mod category. I have already a soluble component that I've added and shown how to in a previous video, and I will use this one S_xt1 as inhibitory component. Then I will need to define an inhibition term, this ISXT1 function of the concentration of this inhibitory component and this K factor, and therefore I will need to define an additional parameter K. And lastly, I will modify the aerobic growth of autotrophic biomass rate equation by adding this factor, this inhibition term, as a factor inside the original rate equation. And I'm going to do all this without writing a single line of code, which is what the model editor allows for. So I'm switching now to the model editor of West, start up my modified block library. And I'm going to directly work on the Gujer matrix. And I'll first start from the last bullet of my slide here. So I will modify the rate equation of the autotrophic growth. This is the process. This is the rate equation. So if I click in that cell, this editor, local code editor pops up, and I can simply type in here multiplied by state dot. State is a keyword in MSL, and you see that if I type in dot, I get a drop down that shows me the available state variables which have been defined in the scope of the Gujer matrix. Evidently, this is not the case for my new inhibition factor. So continue simply to type in state dot I underscore S underscore XT1 F4 to confirm the changes. And now you see that I effectively have modified the rate equation. Now look, if I click on this button here, check for undeclared quantities, what I get from West is a list of state variables that are not declared, that are used but not defined in the scope of the Gujer matrix, in the scope of the conversion model. Some, I know, the scale A actual, the volume, the temp actual, are defined elsewhere, so I can simply uncheck them, but I leave this one so I can confirm, and West will, the model editor will create a template in the state variables page for this new variable that I have just instantiated, just used. Now, in the state variables tab page, I'm going to fill in the relevant information. As a data type, I'm going to use inhibition term, which I know exists. I don't need to specify value, initial value. As an equation, I'll leave this field blank for a second and continue to the description. Here I can just write s underscore xt1 inhibitory effect on autotrophic biomass. Oh, not autotrophic, yes, growth. Oh. Right. The unit will also be taken from the original data type, so I'll leave it blank. The group I'm going to use kinetic. There are a couple of additional attributes here at the end, and I'm going to use this hidden attribute to not visualize, not display this state variable in West at the level of the block details, because it's not strictly necessary. I can, of course, unhide hidden quantities if I want. Now let's type in the equation, and the equation that I'm going to type in is exactly this, with the addition of the necessary keywords. So I'm going to type in parameters, because ksxt1 is going to be a parameter. So parameters dot, again I get the drop down parameter that is not yet defined in this scope, so I simply continue and type in the name, copy this because I'm going to reuse this string, divided by paste plus state dot, again C denotes the concentration vector, bracket S underscore xt, sorry, 1, sorry, st1. Right, and confirm. And now this is the equation that I wanted to have for the inhibition factor. Then again, I click for undeclared quantities. My K factor is detected, so I click on create, go to the parameters tab page, find the template, and fill in what's missing. As data type, I'm going to use saturation coefficient, initial default value, so in this case 20 grams per cubic meter. As a description, I'm going to write S underscore xt1 inhibition coefficient for autotrophic growth. Right, the unit will be taken from the data type, and group going to use kinetic, which already exists. All this is done, so I have effectively implemented this change in the rate equation, defined this inhibition factor state variable, declared this new parameter. What I'm going to do is generate code, and if you recall in other videos where I have a modified category, I did generate code at the level of the category, because I had also changed the state vector. This is another level at which code can be generated. So I'll generate code from here and save my block library. Now to test the effect of the discharge of an inhibitory pollutant and try out the modified ASM model, I have prepared a slightly updated version of the standard nitrification denitrification activated sludge system that you find among the samples in the standard waste installation. So I've started from the 2ASU, opened the project, saved as a different project. And first of all, I have switched the instance from ASM1 temp to my new instance ASM1 mod through the block library setup. Then I have added a separate I have adjusted the influent fractionation model, because now I have, if you recall, in this category 2 additional components compared to the ASM1 temp instance. So I've adjusted the fractionation model. I can show it to you in my project, and I have added a separate input block with the industrial icon to represent the discharge of my potentially inhibitory substance. And I have created a couple of plots which will demonstrate the effect of this discharge. In addition to this, I have also created a small dashboard using some very cool new feature of WES 2016. This part is also covered in a separate video. Through a dashboard, I can very easily, as you will see in a moment, switch from a base situation where there's no discharge to a situation where there is a discharge, and I can visually compare the outcome. So now I'm going to see this, look at this project. You see the layout is the base 2ASU with the addition of this separate input. I've created these two plots, and here's the dashboard. You see I've used a radio button to switch on and off the discharge, and I've also added a field, an input field, to very easily increase or decrease the sensitivity of my biomass, my autotrophic biomass, to this particular inhibitory species. So I can launch the simulation without the reference simulation without discharge. And here's the effluent quality in terms of ammonia and nitrate. You see that the inhibition term is all the time at 1. Now I switch on the discharge and simply rerun the dynamic simulation. Now you see the inhibition term, which has significantly dropped down to 0.2 and has some tail. And if we compare now the effluent quality in terms, for instance, of ammonia, you see that without discharge, this is the level. I have discharge at day 3, and this is the concentration of ammonia in the effluent with discharge, so with the inhibition due to this pollutant. I can show you the effect, for instance, of increasing the sensitivity of the autotrophic biomass to this compound. So I'll reduce I lower the Ks value, rerun the simulation, but let me first, for instance, do this. I'll keep one data series on this plot, rerun the simulation, and you will see now that the dip here is more pronounced. The recovery also takes slightly longer, and the concentration in the effluent is even higher. And this is all I really wanted to show you for this video. Thank you for watching, and please come back for more videos. Goodbye.